Hey guys, let's try and do these two differential equations, free responses in the same video. So whenever we're asked to sketch a slope field, we're going to set up a table of values, but not a traditional table of values where it's plug in an x and get a y value. Instead, we're going to plug in both an x value and a y value. We'll say that my x's run top to bottom and my y's run this way. The x values that we're looking at are -1, 0, 1, and 2. And the y values that we're looking at are 0, 1, and 2. So for each of these ordered pairs, we're looking at what the slope is of the function at those points. And to do that, we're going to plug in our x value here for x and our y values here for y. This one was nice because either time that x or y were 0, our slopes were 0. And then when I plugged in -1 for x and 1 for y, I got +1/2. -1 for x and 2 for y, I got 2. Here I got -1/2, -2, -2, and -4. Okay, so now we just need to plot these slopes, and we don't have to be too exact when we plot non-zero slopes. Zero slopes we should be okay with, in that we're going to plot horizontal lines. So all of these, when y was equal to 0, our slopes were horizontal. When x was equal to 0, our slopes were horizontal. Now for the point -1, 1, so if I'm looking at this point right here, I'm going to go to my table of values. -1, 1 brought me to a slope of 1/2. That's a positive slope where I can aim to go up 1 over 2. So I want to try and aim for this point right here, I guess. So I'm just going to have a non-zero slope that's positive where I'm aiming at that point. The point -1, 2, my slope is +2, so that's a steeper positive slope. Here I was aiming for the point up 1, I guess left 2, so I was aiming for this point over here. -2, so it should be a steeper slope. -2, so this was that same steep slope, and this should be even steeper still. Now when we do these, we don't have to be so concerned with the steepness of it. You can try and get an idea, but what we're really looking for is positive or negative, and then of course the zeros there. So that was our part A. Remember that on the test, you're going to have to copy that slope field into your answer booklet. To write the equation of a line, we need a point, and a slope. We're using the point x is equal to -1, y is equal to 2. So our point is -1, 2. Our slope at that point, if we go to our table of values, -1, +2. So x value -1, y value +2. We're looking at the slope 2. So our equation of our line in point slope form, y minus 2 is equal to m times x minus -1. Okay. So for part C, we want to find the particular solution given an initial condition. So we're working with the differential equation, dy dx is equal to -xy squared over 2, and the initial condition is that when x is equal to 1, our y value will be 2. The first thing that we want to do is we want to separate our variables. So if we want to get this y squared on the other side, we're going to divide both sides by y squared, so I have 1 over y squared dy is equal to -x over 2, and to bring this dx over here to the right, we're going to multiply both sides by dx. Okay. We're now ready to take the indefinite integral of both sides. And it's easy to want to call this the natural log of y squared, but the antiderivative of 1 over y is the natural log of the absolute value of y, but that exponent really could be written as y to the negative 2 dy, and so since that exponent is not negative 1, it's not the natural log. Instead, we use our power rule, where we add 1 and divide by the new exponent. So on the left side, we're going to get negative 1 over y, because if we add 1 to negative 2, we get negative 1, and then divide by the new exponent, which is negative 1. So negative 1 over y on the left side is equal to, well, let's add 1 to 1, negative x squared over 2 times 2, so x squared over 4, plus our constant of integration. And I know that we have a constant on the left side and on the right side, but we rewrite that as a single constant. We're now ready to solve for our constant using the initial condition. X is negative 1, y is 2. So when y is 2, and we want to be a little bit careful on the right side because it is easy to mess up this arithmetic in that the right side is negative 1 squared, which is positive 1, but then we have times that by negative 1. So add 1/4 to both sides. If we got a common denominator, 1 minus 2 is negative 1 over 4 is equal to c. I like to come back to this point here. So now I have negative 1 over y is equal to negative x squared over 4 minus 1/4. And if we look, all of these signs are negative, so we can divide by negative 1, and we're going to have 1 over y is equal to a positive x squared plus 1. And since these already have a common denominator, let's write that as x squared plus 1 all over 4. The reciprocal of y would be 4 over x squared plus 1, and this is all over. Okay. So this took 8 minutes. I think I can do the next one in 7 minutes. Probably just going to fill in that slope field and figure that you guys can see how I got those numbers. Okay, so my slope field was negative 1, 0, 1, 0, 1, 2, and 3. Okay, all of my horizontal slopes were oh no, too fast. I was going too fast. These were both positive, and then this one should be steeper. Okay, so there's my slope field. And now for part B, what they're asking is when will all of the slopes be positive? So if I'm thinking about what my differential equation is, I want to know when this will be greater than 0. So when will x squared times y minus 1 be greater than 0? That will happen. Well, x squared is always positive no matter what I plug in there. or 0, which is why we have all of these. So if I want to know when it's strictly going to be greater than 0, well, this part is always going to be either positive or 0. So we don't have to worry about that. Our derivative is going to be greater than 0 when y minus 1 is greater than 0, or when y is greater than 1. And if you look at these, all of these slopes are of the form y is greater than 1. We should make a little bit of a note on that this is true when x is not equal to 0. That way we're accounting for all of these horizontal slopes here. Okay. And our initial condition is f of 0 is equal to 3. So our first step, let's separate these variables. So if we want to separate these variables, let's divide both sides by 1 minus y. So we get 1 over y minus 1 dy is equal to x squared dx. And we're ready to take the antiderivative of both sides. Get out of here. The antiderivative of 1 minus y is the natural log, absolute value y minus 1. And this is going to be equal to x cubed over 3 plus our constant of integration. Using properties of logs, the absolute value of y minus 1 is equal to e to the x cubed over 3 plus c. Now, because we have addition in our exponent, let's rewrite this as the absolute value of y minus 1 is equal to e to the c times e to the x to the third over 3. But a constant is a constant. Y minus 1 will equal k times e to the x to the third over 3, where k is plus or minus, because of the absolute value symbol, e to the c. So we're going to solve for k where it's a little bit easier to, where we don't have to worry about that constant being the exponent of e, but rather that whole constant there. So now, using our initial condition, 3 minus 1 is equal to k times e to the 0 to the third over 3. 3 minus 1 is equal to k. 2 is equal to k. Green. If I look right here, now knowing what k is, y minus 1 is equal to 2 e to the x to the third over 3. Y is equal to 2 e x to the third over 3 plus 1. And here is our particular solution. Okay, I know that I did that one really quickly, but again, slope field is just kind of plugging and chugging. Part B on this one wasn't bad, and part C, I think that this step here is the most important, this one that I have written in black. And then it makes it easier to solve for that constant. All right, we'll go over this on Wednesday.